Here is a table showing some equivalences between sets. For example, for the identity laws tell us that A intersecting the universal set is equivalent to A. This double arrow means equivalent. And A union with the empty set is equivalent to the set A. Let's prove these. So here is set A. It is a subset of the universal set because the universal set is supposed to include everything that's involved in a particular problem. So A is seen to be inside set U. We can write that like this. A is a subset of U. This symbol is subset. As a matter of fact, A could equal U as well. So we can draw a line here to indicate that A is a subset or equal to the universal set U. But of course A cannot be greater than the set U. In other words, U is certainly not a subset of A, because as I said, the universal set contains everything involved in the problem. So the universal set must contain set A. So what is the intersection of set A with set U? Well, the intersection is the set of elements that are in both of these sets. If you think about it, the intersection must consist of all the elements inside A. Because if an element is in A, it's automatically in U. Any element in the set A is also in the set U. However, if we take an element that's outside of A, this element, well, that means it's not in A. It's inside U, of course, but it's not in A. A intersecting U is a set of all elements that are in both set A and set U, so all the elements in here. So A intersecting U is just A. This is true in general, of course. If we take any subset of a set, say A is a subset of B, we don't have to be talking about the universal set. If A is a subset or equal to B, A itself could be equal to B, then the intersection of A and B is just A itself. The next identity law is actually quite trivial. The union of A with the empty set is just A. Well, the empty set consists of no elements. There's nothing in it. So if we unite those elements with A, we just have A. The intersection of A with the empty set is just the empty set. We are interested in the elements that are in A and also in the empty set. The elements that are in both of these sets are the elements that are in the intersection of the two sets. Well, the elements in the empty set are no elements. So the intersection can at most include all the elements in the empty set. But there are no elements in it, so the intersection of A with the empty set is just the empty set. Now let's look at the union of A with the universal set. A, of course, is a subset or equal to the universal set, so A is contained in U. So if we want to get the union of the elements in A with the elements in the universal set, we just count all the elements that are in both sets. So we count all the elements in A and in the universal set. But the elements that are in A are already in the universal set. So by counting the elements in A, we're just counting the elements in U. By the way, we only count them once, of course. So basically, the union of these two sets is just the universal set. So it's everything. So we could shade in the whole lot. These elements will be counted twice if we just do a raw count. If we count the elements in A first and then count the elements in U, these will be counted twice, so we have to allow for that to make sure that they're only counted once. So if they're only counted once, we have all the elements in here and all the elements in A complement. That's everything outside of A. Well, that's just everything inside U. The next laws are fairly straightforward. The intersection of A with itself is just A. That's almost self-explanatory. The union of A with itself is also just A. The double negation law just tells us something about the complement of a set. Here is set A. A complement is everything outside of A. The universal set is meant to involve everything in a problem, or it could just literally mean everything. So A complement is the region outside of A. So A complement would be this shaded region here. If we get the complement of A complement, that would be everything outside of A complement. Everything that's not in A complement but is in the universal set. So the complement of A complement is just A itself. So A complement complement is A. This is equivalent to the idea of double negation in logic. The commutative laws are more or less self-explanatory. The intersection of A and B is the same as the intersection of B and A. The union of A and B is the same as the union of B and A. Let's look at the associative laws. A intersecting B intersecting C is the same as A intersecting B intersecting C. So when we're intersecting three sets, it doesn't matter which two we take at a time. So let's look at the left hand side here. Let's look at A intersecting B. Or the intersection of A and B is everything inside this red region here, everything in here. That is the elements that are in both A and B. Now if we want to get the intersection of this set with C, well, C is everything inside here. This is also, I'm using red, but what's common to both of them is this region here. It's the intersection of the three sets. Any element that's in here is both in A intersecting B and it's also in C. It's in both sets. Now let's look at the right hand side. Let's do the bit in brackets first. That's what the brackets mean. Well, we look at B intersecting C. So B intersecting C is everything in here. So every element in here is in both set B and set C. Now let's take the intersection of this region with set A. So I'll do A in green, everything inside this green circle here. So what's the intersection? Well, it's everything that's inside the green circle and also inside this blue region, so it's everything that's in here. But that's what we had earlier. So this region is the intersection of all three sets, so it doesn't matter which two we take first. The associative law also holds for the union operator. It doesn't matter which two sets we unite first, we get the same answer. So if we take A union with B, then we have everything that's in A and B. So all this region here. Or I could draw a ring around the whole lot. And we want the union of this region with C. So we just combine it with C. And wouldn't matter which way I do this, of course. I could have taken B and C first and then combine it with A. Makes no difference. In the first distributive law, we have A union with B intersecting C is equivalent to A union with B intersecting A union with C. So we can take A and distribute it in through this bracket here. We can take A union with B intersecting with A union with C. So let's look at a proof of that. So here I have a picture of A union with B intersecting C. B intersecting C is this region here. And of course this is A. So we just unite these two sets together. So we get all this region here. That was the left hand side of the first distributive law. Now let's look at the right hand side. We want to take A union with B and intersect it with A union with C. Well, A union with B is everything in this shaded region. Just unite A and B together. Let's look at A union with C. I'll do that in a different color. A union with C is all this region here. All of A and all of C. And we're interested in the intersection of these two regions, the white region that I shaded and the blue region. So I will do the intersection in red. That's where we have both white and blue. Which is the same as what we have up here. So it shows that the left hand side is equivalent to the right hand side. So that proves the first distributive law. In the second distributive law, A intersecting B union with C is equivalent to A intersecting B union with A intersecting C. So we just distribute the intersection into the brackets here. So let's look at the left hand side. We want to look at B union with C, which is everything here in this region, and get the intersection of B union with C with A. Well, it's fairly straightforward to see that the regions that overlap between A and B union with C is this region in here. Now let's look at the right hand side. We want to take A intersecting B, which is this region here, and unite it with A intersecting C, which is this region here. So we just want to unite A intersecting B, this region, with this region. Put them together so you can see that we have the same region. So these are equivalent. By the way, to get one distributive law from the other distributive law, we just interchange the union and the intersection symbol. So this union becomes an intersection, and this intersection symbol becomes a union symbol. Let's look at the first of De Morgan's laws. A intersecting B complement is equivalent to A complement union with B complement. A intersecting B is this region here. The complement of this region is everything outside of this region. So the complement would be this region here. Everything outside the intersection of A and B. Now let's look at the right hand side. A complement union with B complement. Well, what is A complement? A complement is everything outside of A. So this red region is A complement. And we want to unite it with B complement. B complement is everything outside of B. So I'll do that in blue. So just everything outside of B is in blue. That's B complement. So we want to get the union of A complement with B complement. And you can see what we get. We get exactly this picture here. Unite the red with the blue. Well, that just gives us everything outside of the intersection. So that shows us that the left hand side and the right hand side here are equivalent. To get the second De Morgan law, we replace the intersection in here with a union, and on the right hand side we replace this union with an intersection. So we just interchange the intersection and the union symbols. So let's look at the left hand side of this second De Morgan law. A union with B complement. Well, A union with B is everything inside A and B. So the complement of this region is everything outside it. Now let's look at the right hand side. We want to look at A complement intersecting B complement. Let's first look at A complement. That's everything outside of A. So I'll do A complement in red. We want the intersection of A complement with B complement. B complement is everything outside of B. So I'll do B complement in blue. So we want the intersection of the red region with the blue region. If you look carefully here, the region that is both red and blue is everything outside of A union with B. In other words, it's A union with B complement. So that shows that the second De Morgan law holds. This first complement law is very straightforward. Here is set A. A complement is everything outside of A, and if we take the union of A with A complement, we just put these two sets together, we just get the whole lot, the universal set. We can very easily see that set A and set A complement have no elements in common. That means that the intersection of A with A complement is the empty set. So we've now proven the two complement laws. By the way, if the intersection of two sets is empty, the two sets are said to be disjoint. The complement of the empty set is just the universal set. That makes sense. Everything outside the empty set, well, there's nothing in the empty set. So everything outside of the empty set has to be the universal set, and vice versa actually. The complement of the universal set is empty. The universal set includes everything, so its complement is everything outside of it. Well, there's nothing outside of everything. So U complement is the empty set. A intersecting A union with B is A. Well, A union with B is all this shaded region here. And if we take the set A and intersect it with A union with B, that means we want everything that's both in A and in A union with B. Well, that's just everything that's in A. If we take any element in A, then it's not only in A, it's also in A union with B. So that's fairly straightforward. We can swap the intersection and the union symbol around to get the second absorption law. A union with A intersecting B is just A. Well, A intersecting B is this region here. And if we get the union of A with this region, well, A is this red region. So we unite the white region with the red region. Well, that just gives us the red region. That just gives us A.